Today, I will introduce our method called CCMNet, which leverages calibrated color correction matrices to solve the cross-camera color constancy problem. This work was done in collaboration with Yonsei University and Samsung AI Center Toronto. For the cross-camera color constancy task, we propose a novel module called Camera Fingerprint Embedding, or CFE. In addition, we further propose imaginary camera augmentation, a new data augmentation strategy that enhances the generalization ability of our model. As a result, our method achieves state-of-the-art performance, is lightweight, and runs about twice as fast as existing approaches. Computational color constancy, also known as auto-white balancing, is the task of predicting the global illumination color for a given raw RGB image. However, due to the different spectral sensitivities of imaging sensors, images taken with different cameras of the same scene often have very different color distributions. This sensor-specific variation leads to what we call the camera dependency problem in learning-based AWB models. A color correction matrix, or CCM, records how each camera responds under canonical illuminance. For each camera, CCM are usually calibrated under two standard illuminants, D65 and A. For illuminants that fall between these two color temperatures, the corresponding CCM can simply be obtained by interpolating between the two calibrated matrices. In short, CCM are essential information that precisely describe how a specific camera perceives colors, and this motivates us to ask, can we use them to achieve cross-camera generalization? Cross-camera color constancy aims to train a model that performs robustly on images captured by any camera, even those unseen during training. A previous approach called C5 tackled this by using 6 to 8 additional images captured by the same camera as guidance at training and test time. However, this reliance on extra guidance images comes with instability. When the guidance images change, the model's predictions inevitably fluctuate, leading to inconsistent results. Since the color correction matrices encode the unique color response characteristics of each camera, we propose to replace the guidance images of C5 with the calibrated color correction matrices that are already available for each device. Concretely, we first convert a set of predefined illuminations into camera RGB values using the CCM, forming what we call an illumination locus that is unique to each camera. Because the CCM are fixed and camera-specific, this transformed locus changes when the camera changes. Next, we encode this device-specific illumination locus into a compact 8-dimensional feature, which we call the Camera Fingerprint Embedding, or CFE. This embedding serves as a dynamic guide that can adapt to varying camera inputs during both training and testing. Ultimately, the CFE is integrated into the convolutional AWB backbone known as CCC, thereby enabling strong cross-camera capability without the need for extra test time images. In addition, we leverage the linearity of color correction matrices to introduce the concept of an imaginary camera as a data augmentation technique. For example, given images captured by cameras A and B, we interpolate not only the two images themselves, but also their corresponding matrices in the same ratio. Through this augmentation, the model is exposed to infinitely many virtual cameras during training, thereby significantly enhancing its generalization ability. For training and testing, we employed 4 multi-camera datasets, using 3 for training and 1 for testing in a leave-one-out manner. This ensures that the model is always evaluated on completely unseen cameras. Quantitatively, our model achieved state-of-the-art performance in cross-camera zero-shot evaluation, outperforming previous methods in accuracy. Moreover, by utilizing the stable guidance obtained from calibrated color correction matrices, our model produces consistent predictions across different cameras without the instability issues seen in prior approaches.